can compare to the third unit or any other unit. So let us look at this topic of AV trees as well as B trees. Now this B trees, you might have heard this term in your DBMS or database management system. These are actually, B tree is a generalized form of multi-way trees, and this is actually used for efficient storage of data or efficient utilization of memory. Now, just like we have binary search trees or binary trees, which has at most 2 children, then we have binary search trees, which also has at most 2 children, but there is a condition that the left child is less than the root and right is greater than the root or its parent. Now, the problem with the binary search tree is that as the nodes are created, its height gets increased, in a very random fashion. And when the height increases, what actually happens is that there will be a lot of comparisons that has to be made. So to make retrieval efficient or to make searching efficient, the height of the tree must be in a balanced way. Now, when we say height of the tree should be balanced, that means the tree itself should be a balance. That is the right subtree, and there should not be a large difference in the height of the right subtree when compared to the height of the left subtree. So this is where balanced trees, the concept of balanced trees comes into picture. So there are several balanced trees. We have AVL tree, we have red-black tree. In the same way, we have something known as AB trees, or what we have is multi-way search trees. Now these multi-way search trees are also balanced trees. There are different ways and concepts that we apply or logic we apply to balance the search trees. So AVL is one thing, red-black tree is another, and then we have another concept, another logic known as multi-way search trees. So AB trees are part of multi-way search trees. Here, AB are two constants, two integer constants. Now, A is nothing but should be less than equal to B. No, sorry, less than equal to 2. That means at least it should be 2. And A should be less than B plus 1 by 2. Now this type of a multi-way search tree is nothing but, it's called, one of the example, it's called as 2-4 trees, where 2 is A and 4 is B. Or it is also called as 2-3-4 tree. 2-3-4 tree. And 2-4 tree and 2-3-4 tree is same. So generalized form of that is AB trees. Now the properties of this AB tree, this kind of a multi-way search tree is that, there are two properties. One is the size property. The size property says that each internal node, obviously external node will not have any children and leaf nodes will not have any children. So the size property says that each internal node has at least a children, at least a child, and at most B children. There is a spelling mistake here. At least a child should be child over here. Oh, sorry, not child. Sorry, it's a mistake. It should be it should have A children and at most B children. Sorry, I also got confused over here. Now A is nothing but, I should have actually, I'll just do one thing. And here itself I'll make this thing as bold. or in brackets. I'll put this part, brackets bold, so that nobody has confusion. No, the root node gets problematic. Anyway, let me just slide it to the side. Let me just increase its size. And why I'm having a problem here? Some of the students are trying to join from outside MGCD. I don't know why. Okay, anyway, it doesn't matter. Let us continue our work. So here, even I got confused here, actually. The size property says that each internal node has to have at least A children. A children, A is, if A is 2, at least 2 children. And at most B children. So if B is 4 or B is 5, can have at least 5 children or 4 children, except the root. Now, this condition except the root, we will try to see by taking an example. The other property is the depth property, that all external nodes have the same depth. Now, using this depth property, we can guarantee that the AB tree will be a balanced tree. So when all the external nodes are at same depth, means the height of the left as well as the right subtree are equal. Now this leads to a generalization of AB trees. That is what I told you about. It's called as 2-4 trees, where 2 is A and 4 is B, or 2-4 trees are sometimes also called as 2-3-4 trees. So let us try to take the value of A as 2 and value of B as 4, and let us take an example and look at how these AB trees are created and how they work and how they are balanced. So we call this as 2-4 trees. A is 2, B is 4. Now let us consider we have these elements: 4, 6, 12, 15, 3, 5, 10, and 8 that needs to be inserted. Or we have to create an AB tree of these elements. Now, when we say 2-4 trees, that means at least A children. A is 2. So this node, every node of the AB tree will have at least 2 children and at most 4 children. So if you look at this node, we have 4 children, means if we just look at each vertical line, this can create a child. Then this vertical line can create another child. This can create third child, and the last vertical line can create the fourth child. So here, when we have 4 children, how many possible keys or how many possible data items can be stored in this node? There can be 3 data items that can be stored. So that is why sometimes this is called, I told you, 2-3-4 trees. 3 is nothing but 2 and 4, the extreme 2 values gives us the number of children it can have. And 2-3-4, we say third, the middle part tells us how many keys it can have or how many data items it can have. So when we have at most 4 children, that means a node can have at most 3 keys, can store at most 3 keys. So initial node will be the root node. It can store 3 keys, as in general binary search tree. Only 1 key or 1 data item can be stored in the node. Whereas in this AB trees, when we have 2-4, that means at least 3 keys can be stored in a single node. So first element is 4. So we have space, we are storing 4. Then we need to insert 6, or we need to create it. Next item is 6, so we need to create. So there is a second space vacant over here in the same node. So we will create, this is a part of the tree. I'm showing it section wise. When 4 is inserted, the node, this is the node. when 6 is inserted, there is a space after 4, so 6 will be the next element stored, and still there is only one node, though two elements are stored in the tree, but node is only one. Then 12 is there, so there is a space available, so we can store 12 in the same tree. Then 15. When 15 comes, this is still the root node. When 15 comes, 15 has to be stored after 12 because it's greater than 12. And remember, multi-way search trees also follows the same property of a binary search tree. That is, the element has to be, the greater element has to be to the right of the root, and smaller element has to be to the left of the root. So now when we have 15, what happens in A-B trees is, now when we are trying to store an element, when there is no space in that node, that means there is an overflow. Now when overflow occurs, overflow of data, when overflow occurs, the node will be split. So this node, this is a root node, 4, 6, which contains 4, 6 and 12, will be split up into two nodes. So we have 4, 6 from this part, and 15 has to be stored. So 15 is stored. Actually 12 should be over here, 12. But when it is split up into two nodes, then there should be some node connecting these two nodes. There should be a parent for these two nodes. So that parent will contain 12. That is the element which was just before the element which we were trying to insert. So 15 we were trying to insert. So 12 is just before 15. So 12 goes up and gets stored in a new node. And this node becomes the root node. And you can find that we have these lines represent. So all the elements to the left child of 12 are smaller than 12, and all the elements to the right are larger than 12. So whenever there is an overflow, that is an element has to be inserted and there is no space in the node, then that node gets split up into two nodes. And the element which is to the left of the element we are trying to insert, that element goes into a new node. Now remember here, when we compare with binary search trees, whenever we insert elements in the binary search trees, we try to create a node below the tree and then assign it to a parent. A new node comes, we try to insert it below the tree and then create its parent. So the tree grows from root to the leaf nodes. But here in multi-way search trees, or in 2AB trees or 2-4 trees, the tree, multi-way tree or AB tree, grows from leaf nodes to the root node, exactly in opposite way. Now let us try to insert 3. Next element we need to insert is 3. We need to create a multi 3. Now where should 3 come? It is less than 12. 3 is less than 12. So obviously it has to go into the left node. Now it has to go into left node. The first element is 4. So it has to, element 3 has to be to the left of 4. Now, should we create a node here? Or should we split this node, or should we create a new node? No, we will not create a new node. Why? Because when 3 comes here, there is still space available in this node. So what happens is 6 gets shifted to the right, 4 gets shifted to the right, and 3 will be inserted or will be stored in this place. So when there is a space, the elements are shifted, to conform to the property that all the elements to the left are smaller than to the right. Then the next element is 5. Now, this is a part of the earlier one. We are trying to insert 5. 5 gets inserted, has to be inserted between 4 and 6. Now, is there an overflow here? Is there an overflow here or not? Is there an overflow here or not? There is an overflow. When there is an overflow here, what happens is, as I told you, what is happening here? Okay. And there is an overflow. Which node? This 3, 4, 6 node has to be split. So there is an overflow here at this node and the left node, left child, and the left child has to be split. So we split the left child into 2. 3, 4, and 6 gets moved here because 5 has to be stored at this place. So 15, this node with 15 is the original node. 3, 4, 6 node has been split into 3, 4 with one node and 6 with another node. And then 5 comes here, actually. 5 comes here. But since we are splitting this node, 5 goes to the root because root has space. And 5 has to be built, is smaller than, so 12 gets shifted and we have 5 as the first key. Now, if you look at this part of the tree, we have in the root node 5, all the elements to the left, that is the children of left, are smaller than 5. You can see it's there. Then all the elements to the right of 5 are greater, so 12 is greater. And to the right, its right child is 6, which is greater than 5. Then for 12, 6 is the left child, which is smaller than 12. That is fine. Then the right child has 15 to 12. For 12, 6 is the left child, 15 is the right child. So it's greater than, so we are conforming to the properties of the left should be less than the right. Now I have drawn this node over here because of the space constraint. And the next thing we need to insert is 10. Now where does 10 get inserted? This was the previous tree. In this previous sheet, if 10 has to be inserted, we will look at 5, it's greater than 5. We will look at 12, it's less than 12. So it has to obviously between 5 and 12. So it has to be inserted in the node. It has to come at this place, which has node 6. Is there a space in the node which has 6? There is a space, so 10 can directly get inserted here. And all properties are satisfied. Again, we have 8. Now, where should 8 get inserted? 8 will be inserted, should be inserted after 5, and it's less than 12, so it has to be inserted between 5 and 12, which is this node itself. And this node has space because there's 10 here, 8 here, so it has to come between 6 and 10, 8. There is a space, so 10 gets shifted here, 8 will be assigned. So this is what is about AB trees or 2-4 trees. Now here we have taken A as 2 and B as 4 and seen this example. But suppose A was 2, B was 6, then there would be at most 6 children. So you can store at most 5 keys in one node. When you store at most 5 keys in one node, then you can see that 4, 6, 12, 15 and 3 will be stored in one node, all 5 keys with 3 as the first key, 3, 4, 6, 12, 15. Then 5 has to be inserted, so that node will get split into node with 5 more keys and 5 more keys. So AB is a generalized form of 2-4 trees. So how we perform operations in 2 4, how we create trees in 2 4 trees, the same way we have, I mean, we can create for any A and B values. So this is what is about A-B trees. Now why is this A-B trees used? Because when an element has to be searched or when the data has to be searched, it will take O of log n time to search. Same as with the, but I mean the as same efficiency we have as with respect to the other balance trees. Now here n is the number of nodes which gets created. Obviously, if you see, there are how many elements here? 8 elements here, I suppose, or 7. 1, 2, 3, 4, 5, 6, 7, 8 elements. So for these 8 elements, we are able to store all these 8 elements using 4 nodes. But whereas if you would have taken binary search trees, we would have 8 nodes. Not only binary search trees, if you if suppose if we consider even the balance trees itself, like AVL tree or any other kind of a balance tree like red black tree, what we have is we will be needing 8 nodes to store. That will be consuming memory space. But in multi-way search trees or in this 2 4 or AB trees, because we are saying that a node can have at least A children and at most B children, then the number of keys what we can store is between, I mean, it's 1 minus B. So that is how the number of nodes what we need will be less and it will be consuming less amount of space, whereas giving us the same time complexity of log n. Now let us talk about B trees. B trees is also a multi-way search trees. Actually, it's like a B tree where there is a condition that A should be half of B. Now here I have written this definition this way because actually it is A should be half of B. But as, I mean, theoretically it is said that if D is equal to B, if B is equal to D, then A is equal to D by 2. It's the same as saying A is equal to B by 2. So such that we have at least we have half of the children of at most children. That is what is a B tree. Now here D is nothing but degree of the tree. Now degree is how many the children it has, or the maximum number of children gives us the degree of the tree. So here D is the degree of the tree. So AB tree will be a B tree when A is half of the degree of the tree and B is equal to the degree of the tree. This is just the what you call a theoretical part there. Now the other thing is obviously when B is D, according to AB tree definition, a tree should have at most D children, or at most the degree of the tree. Children at most to the degree of the tree. So B is, kind of an AB tree which has more, it's a little better than AB tree when the degree of the tree is concerned and when A is half of the degree and B is the degree of the tree itself. Now, why this concept of another concept of AB trees is that they say that it gives a little better performance than AB trees when the degree of the node is concerned. How is it better? The two AB trees has a complexity of O of log n for search in a node. or searching an element. Now B trees say that it has the complexity of O of log n to base B. Now what is this B? Base B is the number of children it has. So that is what they say, that it has a little better complexity than 2, 3 or 2, 4, 3 or 2, 3, 4 trees. So AB tree is a generalized form of AB trees, and AB trees is a generalized form of multi-way search trees, where we should remember that A is at least those many children, and B is at most that many B children, except the root node. So that is what is all about AB trees and B trees. Remember, mostly they are used for efficient utilization of memory space. When files are stored, when disks in the disk, when large amount of data is stored in the disk, the AB trees are used to store that data so that the searching of the data is much efficient and much easy.